All right, so we're going to pick up here with kind of solving for this concept of entropy. So remember that we talked about, okay, I can look at something and, oh, it went from a solid to a gas. That's more randomness, more disorder. But also, we can put a number on these values, actually say, okay, here's the number, so I can use it in a problem or mathematically. So couple things here. So we're just talking about thermodynamics. So I put that definition in here. Not super duper important, but get down here. It says number two. It says in general, the more atoms in a molecule, the greater the entropy is going to be. And so if you just have lots and lots and lots of pieces, it's going to be hard to be ordered. And so more disorder. So we'll just put the word greater in here. Now remember, most likely on assessment, you're not going to be doing definitions, you're going to be doing problems. And so that's where the problems become more important. So now this is, again, we saw this with the delta H, but the standard molar entropy, or S, is the entropy for 1 mole of a substance at its standard state. And so the key words here are 1 mole, which means that your balancing is important because your coefficients are important. And so the numbers in front are going to mean something. So if you look at the formula, look at this. Wow, products minus reactants. Products minus reactants. That is just the theme that you want to stick with. And remember, all of this stuff here just means that we're going to add them up, and then we're going to multiply by their coefficients. All of that being extremely important when you're doing things like this. And so down here we're going to see a problem, and it says calculate the standard molar entropy. So just want to remember that means we're looking for change in S, right? So S is what we're looking for. And so why did it give us 25 degrees? Just to tell us that the temperature is not changing. And there's the reaction. So let's check to make sure it is balanced. And so if you go through this, you're going to see it is balanced, which means that when we multiply times the S values, products minus reactants, we're just going to be multiplying by 1. Now, I do want to point out one thing. Joules, this is going to give us a value in joules, and that's going to be a bit of a problem kind of later on. But right now, it just that's going to be the unit. Instead of kilojoules per mole, is joules per mole. So, all right, products minus reactants. And so once again, that's the theme of this last two sections, is constantly dealing with products minus reactants. Okay. So let's take a look at the products first. And let's go ahead and do 1, because there's only one carbon dioxide. And here's carbon dioxide times 213.6. And let's add that to 1 times the hydrogen. And notice this is hydrogen as a gas. And so I want to point out that unlike delta H, elements in their standard form do have a value for S. So this would be a 0 if it was a delta H, but it's a delta S, so it does have a number. So 130.6. And let's go ahead and bracket that. And then let's go products minus reactants. So let's go 1 times 197.6, and that's the carbon monoxide, plus 1 times the water. So we did that. Now there's the water, 188.7. And then again, I'm going to bracket it. And that's it. Products minus reactants. Super straightforward. So let's run it through. These are easy as long as you remember to do the correct formula. And usually we're fine with it because like there isn't anything that we deal with that's reactants minus products. So, okay. 213.6 and then plus the 130.6, and we hit enter, and now we're going to hit minus in parentheses the 197.6 plus 188.7, and we hit enter. Okay. Obviously, this one is not as complicated because you don't have any coefficients here, but this is going to be a final answer is going to be the delta H is negative 42. Oh, sorry, not delta H, sorry. Delta S. Delta S, sorry. Delta S is negative 42.1, and it's joules. And so understanding that when we find this, that it's going to be in joules per mole as opposed to kilojoules. And that's going to be a real problem later on. So just make sure that you note that. So that unit is important. So products minus reactants, products minus reactants. So if you can remember products minus reactants, you're going to do fine. Okay, try this one on your own. Pause the video and go ahead and work this one on your own. Same kind of thing. Just make sure that you do balance before you do everything, because this one is not balanced. So I'm just going to point out that you do need to go ahead and balance this one. All right, off you go. All right, let's see if you got it balanced first. So let's go ahead and plug in some values. So when you're running this through, the nitrogens, you could put a 2 here. That'll end up giving you 6 H's, so you can put a 3 here. That ends up giving you 3 O's. Well, 3 O's is a problem because we're going to have a hard time getting 3 and 2 to work, so we're going to have to go to the common number between 3 and 2. So I'm going to shift this for the O's over to a 6. I'm going to shift this to a 3, but that's going to mess up my H's. It's going to make them 12. So let's go ahead and put a 4 here, and then there we go. So kind of a back and forth one, but the numbers you want for the balancing are those. You want the 4, 3, 2, and 6. Okay, here we go. Hopefully you remember the trick. Products minus reactants. All right, so here we go. Let's run it through. So we're going to start with the nitrogen, the 2 nitrogens, and it's right there. So I'm going to go 2 multiplied by 191.5. And let's look at the water. So 6 times 188.7, so 6 water, so multiply it by 6. Going to bracket that minus, you can do the NH3, so 4 times 192.3 plus then the oxygen. So here's the oxygen right here. 3 multiplied by 205.0 bracket, and there we go. So the difference in this one is that on the ones you guys have been working, these were all ones. Now we were still writing them down. It's just that you didn't have coefficients deal. So the math is going to be trickier on this one. So this one is ones where I would highly suggest that you do it twice if you have time on a test or whatever, so that you don't make a mistake. So here we go. 2 multiplied by 191.5, hit enter. Add that to, in parentheses, 6 times 188.7, close your parentheses, hit enter, minus, in parentheses, 4 times 192, actually double parentheses, so in parentheses again, 4 times 192.3, close that one, plus, open a new one, 3 times 205.0, close. So once again, guys, just use your parentheses on this second part. So like I don't have my calculator to show you, but just make sure that when you are doing this second part, that like it really, like on my calculator, I'm just making sure that I'm not messing anything up. So it's kind of like this. So like a calculator, you don't have a bracket, but like if we were just writing it out, it would be bracketed there. Anyway, just don't want you to mess up the math. So, okay, run all that through, and it looks like you've got 4 sig figs. So we're going to go that the delta S equals 131.0. And again, paying attention to this joules unit here. Right there. All right, there you go. That's finding delta S mathematically, and that is pretty straightforward. And so now we're going to shift into something new, which is going to be Gibbs free energy, which is going to tell us whether a reaction happens or not, and is also the last topic. Has quite a few little examples, but is the last topic. So you can go ahead and pause this video, and we'll start up on the next one.